Hi everyone, and welcome back to the MCAT A series of lectures in physics. In today's lecture we are going to be looking at forces and equilibrium. In the previous lecture I introduced the idea of vectors before discussing various vector types that you must know for the MCAT. Two of these vectors that I talked about were force and acceleration. Today's lecture will focus on the relationship between these two types of vectors. To develop this relationship, I will introduce Newton's three laws. Each law in their own way gives us a better understanding of how force is related to acceleration. Then, to answer actual questions in the MCAT, we need to be able to visualize how force is related to acceleration. To do this, I will introduce what is known as free body diagrams. Finally, as in the last lecture, I will finish off by introducing something to do with circular motion. This time, I will discuss torque, which is, if you like, the rotational version of a force. To begin, let us now look at Newton's first law. To put it simply, Newton's first law says that a body will remain at rest or moving with constant velocity unless an external net force acts upon it. What does that mean? Well, we can consider an object M that is just sitting on a table. That object will remain on the table, not moving, unless an external force acts upon it. For example, we could consider pulling or pushing it, or we could also consider removing the table and allowing gravity to push that object towards the ground. Not only this, but an object that is moving at a constant velocity will also remain at that constant velocity unless a net force acts upon it. This is a scenario that we are not too used to seeing in the real world. For example, we can imagine a soccer ball going across a field. Eventually that soccer ball is going to stop. This is because an external force, friction, has acted on that ball. Friction is a force that resists motion, and that is why the soccer ball slowed down. In general, it is very hard to totally get rid of friction. For example, if you are at an ice rink and you push yourself away from the wall, even in that scenario, you will eventually slow down. While the frictional force is less on the ice rink, it is still present. Newton's first law is therefore telling us that any time there is a net force on an object, we get an acceleration. Therefore, since Newton's first law is telling us that there is a change in velocity anytime there is a net force, we therefore get an acceleration. Acceleration, remember, is change in velocity. Remember, however, that this only occurs if there is a net force. What do I mean by net? Well, again, consider an object of mass m. If we have one pushing force of magnitude capital F and one pulling force of magnitude capital F, the object will remain in place because there is no net force on the object. All forces cancel out, the net force is zero. Similarly, if we have a pushing force and a pulling force that are not at the same angle, well, in that case there is going to be a net force because there is a net force in a certain direction. As long as there is a net force in a certain direction, we will get acceleration or deceleration in that direction. Moving on from this, now that we know that a net force causes acceleration, we would now like to be able to relate that net force to the acceleration. Newton's second law allows us to do this. Newton's second law states that the net force capital F on an object of mass m is equal to that mass multiplied by the resulting acceleration. This is a vector equation. A vector is equal to a scalar multiplied by a vector. And immediately you can see why we needed to introduce those mathematical tools in the last lecture. We have to be able to do scalar multiplication to deal with this equation. Remember, multiplying a scalar by a vector does not change the direction of that vector. Therefore, this object will accelerate in the same direction as that net force. We may write this equation as A is equal to F over m. And notice that this is a direct relationship between all three quantities. That means that if I was to double the force, then the acceleration would naturally double. As it's A is equal to F over m, if I was to instead double the mass, then the acceleration would halve. And that makes intuitive sense. If the object was heavier, it would be harder to make it move. Things can naturally get more complicated if there is more than one force, as then we would have to calculate the net force first. We will see examples of this being done at the end of this lecture, as well as in the sample passages we have provided for you. The statement for Newton's third law is something you may have heard of before. For every action, there is an equal and opposite reaction. What does that mean in terms of forces? That means that the force that A applies to B is equal to minus the force that B applies to A. To understand this, let us consider an object that is sitting on a table. What forces are on that object? Well, that object is in a gravitational field. It is on the Earth, so therefore it has some weight. That weight points towards the ground, or more specifically towards the center of the Earth, so we represent that by a down arrow and give it the name capital W for weight. Is this the only force acting on that object? Well, it can't be, because according to Newton's second law, there would be a net force and therefore there would be a net acceleration. However, this object is just sitting on the table. It is not accelerating towards the center of the Earth or the ground. Therefore, as the object is just sitting there doing nothing, its acceleration is zero, and therefore the net force, according to Newton's second law, must also be zero. The only way this can be true is if there is a force acting in the opposite direction of equal magnitude. That force we call the reaction force, and we label it with capital R. The reaction force is the force the table is exerting on the object so that the object does not go through the table. On a microscopic level, this is due to all the atoms in the table. These atoms are chemically bound together and therefore not allowing the object to go through the table. This is only one example of a reaction pair as they are known, and we shall see other examples later in this lecture and in the sample passages. The scenarios I presented so far are very simple examples, one force acting on an object. However, in general, there can be multiple forces acting on an object. In these cases, we have to be careful with the left-hand side F. Remember, that left-hand side F is the net force. We need to work out what the net force on the object is before we can apply the equation. To help us visualize the net force on an object, it is a good idea to draw a diagram. Diagrams that show the forces on an object and the resulting acceleration are known as free body diagrams. To demonstrate a simple free body diagram is that of an object falling through the air. Again, this object has mass and therefore has an associated weight, which we label with capital W. In this case, the object is obviously accelerating. It is accelerating towards the ground. In the ideal case of no air resistance, this is the only force acting on the object. In this case, the acceleration A is simply small g. It is that 10 meters per second squared that we discussed in the previous lecture. However, in general, there are other forces acting on this object. For example, as the object is going through the air, there is also air resistance. Because this air resistance is resisting the motion and slowing the object down as it falls, we represent this with an arrow pointing up. The air resistance force is opposing the acceleration of the object, and therefore acts in the opposite direction to the acceleration. However, in general, the object is still falling down, so overall, the weight force must still be bigger than the air resistance force. I have signified this by drawing this up arrow smaller than the weight vector. What this therefore does to the acceleration is it makes it slightly smaller than small g, and therefore this black arrow in general is slightly smaller. Let us consider something that is hanging from a ceiling. For example, it could be a light bulb. What are the forces acting on that light bulb? Well, that light bulb is not moving, its acceleration is zero. That means its net force must also be zero. However, remember, net force being zero does not mean that there is no forces acting on the object. Instead, it means that the sum of the forces in a particular direction is zero. What are the forces on this object? Well, again, this object has mass and it is in a gravitational field as it is on the Earth, therefore it has some weight. That weight, as always, points towards the center of the Earth, points towards the ground, and we give it a label capital W. Again, this cannot be the only force acting on that object, because according to Newton's second law, this object would then be accelerating down. Instead, according to Newton's third law, there must be a force acting in the opposite direction of equal magnitude. This force is the force that the rope or the string that the object is attached to is exerting on the object. The force associated with a string or a rope is known as tension capital T. Now we have all our forces labelled. We have the weight acting down trying to pull the object towards the ground, and we have the tension acting up keeping it where it is. Therefore, to signify that this object is not moving, I shall also write down that the acceleration is equal to zero. Now I have completed the drawing of the free body diagram. I have all the forces labelled and I have stated what the acceleration of the object is. I have already mentioned objects that are simply sitting on a table or objects that are hanging from a ceiling. Such objects are said to be in equilibrium. Equilibrium because there is no net force acting on that object and hence the acceleration is zero. However, there are two different types of equilibrium that you must be aware of. The first is known as translational equilibrium. Translational equilibrium means that the object does not move from one place to another. For example, going back to our object hanging from a ceiling, naturally that object cannot move anywhere because it's attached to a rope, and therefore we say it is under translational equilibrium. However, just because it is not moving from one place to another does not mean that that object is not moving at all. For example, we can consider spinning that object. If we spin that object, the object still remains in the same place, however, it is moving in some fashion. In that scenario, the object is still said to be under translational equilibrium because it is not moving from one place to another. However, what is not true about the object anymore is that it is no longer under rotational equilibrium, the second type of equilibrium you need to know for the MCAT. When an object is hanging from the ceiling and spinning, its acceleration is still zero, but what is known as its angular acceleration is no longer zero. In other words, the net force on the object is zero, but the net what is known as torque is not zero. Torque is the rotational version of force. Anytime there is a net torque, it will cause an object to rotate. The equation for torque is given as follows. Torque, which we label with this Greek letter tau, is equal to the cross product of r and f, which is equal to the magnitude of r multiplied by the magnitude of f multiplied by sine of the angle between these two vectors. What are these two vectors? Well, f is the typical linear force we are accustomed to, and r is the distance between the object and where we apply that force. To make this a bit clearer, let us now consider a door handle. When we are pushing on this door handle, we are applying a force F a certain distance r away from where that force actually acts. In that case, if we assume that the door handle is horizontal and we are applying a vertical force with our hands, we are pushing our hands downwards, the angle between r and f in that case would be 90 degrees, and therefore sine of 90 would be 1, and the magnitude of the torque would simply be the force multiplied by the length of the handle. Again, to find the direction of the torque, we would use the right-hand rule we introduced in the last lecture. If you don't recall this, please have a look again back at our last lecture, or have a look at some diagrams online of the right-hand rule. To finish this short lecture, let us now discuss some questions that commonly come up on the MCAT about forces. The first question is testing our knowledge of Newton's second law. According to Newton's second law, force is equal to the rate of change of which of these following quantities? Acceleration, mass, momentum, or velocity? Well, let's recall what Newton's second law states. It states that the force, or more precisely the net force, is equal to mass multiplied by acceleration. Therefore, the net force cannot be equal to the change of either of these two quantities. It is instead directly proportional to both mass and acceleration. Therefore, we can rule out acceleration and mass. Taking a look at our fourth option, what is the rate of change of velocity? Well, let's recall the definition of acceleration. Acceleration is defined as the rate of change of velocity per unit time. Therefore, force cannot equal the rate of change of velocity because that would mean that force is equal to acceleration, and that we know is not true from Newton's second law. Hence, we have ruled out options A, B, and D, and this only leaves us with C. Force must be equal to the rate of change of momentum. Momentum is something I have not discussed yet, but momentum is actually equal to mass multiplied by velocity. The rate of change of mass multiplied by velocity is mass multiplied by acceleration, which is equal to net force. This second question is testing our knowledge about equilibrium. An object is said to be in translational equilibrium only when the net force on the object is zero, the net torque on the object is zero, both the net force and torque on the object is zero, or neither the net force nor the torque on the object are zero. Well, let's recall what equilibrium and translational equilibrium means. Translational equilibrium means that the net force on an object is zero. Rotational equilibrium, on the other hand, means that the net torque on the object is zero. This means that option B cannot be correct because option B states that the net torque on the object is zero, which can be true for translational equilibrium, but this is not the only time when translational equilibrium is true. Similarly, option C is not correct because having both net torque and net force 0 is not the only case we can have translational equilibrium, because we can have translational equilibrium without the net torque being 0. And finally, option D is obviously not correct because we need the net force to be 0, so we cannot have neither the net force nor the net torque being 0. Hence, the answer to this question must be option A. An object is said to be in translational equilibrium only when the net force acting on that object is 0. This third question is revolving around Newton's third law. The question is asking us about an object on a table, in this case a cup sitting on a table. It is asking us which of the following statements is true about that cup on the table. Is the only force acting on it gravity? Does it exert a force on the table? Is it accelerating towards the center of the earth? Or is it not under rotational equilibrium? Well, again, option A can't be true, because if option A was true, according to Newton's second law, that object would be accelerating. It will be accelerating in the same direction as that force, towards the ground. However, we know that that object is just sitting on the table and not moving. Because that object is not accelerating, the net force must be 0. The only way the net force can be 0 is if there is an equal and opposite force acting in the opposite direction to the weight. This force, remember, is known as the reaction force. Using the same logic, option C also cannot be correct. The object is not moving and therefore not accelerating. For option D, recall what is meant by rotational equilibrium. An object is under rotational equilibrium if the net torque on that object is 0. In other words, if the object is not rotating. As this cup is not rotating, it is therefore under rotational equilibrium. This therefore leaves us with option B. It exerts a force on the table. Again, this option makes intuitive sense. Because the weight of that object is pushing down on the table, it is pushing on the atoms in the table, it is naturally exerting a force on the table. The fourth question is asking us to find the net acceleration of a system of objects that are connected in some way. We are told that an object of a certain mass 6 kilograms is sitting on a smooth table. Smooth, you will see this word again in the MCAT, smooth means there is no friction. Attached to one end is an inelastic string. Inelastic just means that you can assume that the string doesn't stretch. If the string was allowed to stretch, that question would become even more complicated, so much so they would not be expected to know how to do it for the MCAT. We are then told that that string goes to a smooth pulley, again smooth, no friction associated with the pulley, at the end of the table. On the other end of the string hanging down from the table is an object of mass 4 kilograms. When the system is released, the 4 kilogram mass that is hanging from the string will naturally begin to fall. As this 4 kilogram mass is attached to the other mass, that other mass will also begin to move. Both of these objects will accelerate, and we are asked to find the acceleration. How do we calculate the acceleration of the system? Well, anytime you're presented with a question like this, a system of objects, you should always draw free body diagrams for each object. Let us first look at the 6 kilogram object. I will first redraw the 6 kilogram mass over here, and then I will work out what forces are acting on the object. Well, first of all, as the object has mass, it naturally has a weight. Again, that weight points towards the center of the earth, so I will represent it with a down arrow and capital W. As we have discussed many times by now, because that object is not accelerating down, there must be an equal force in the opposite direction, the reaction force capital R. That force is the force exerted by the table on the object to keep that object from falling down. Are these the only forces acting on that object? Well, if they were, that object would stay in place because the net force on the object will be 0. However, we know that object is going to move to the right. It is attached to a string, which itself is attached to an object that is falling. Therefore, because it is attached to a string, there must be some sort of tension. That tension force, capital T, points in the direction of motion, and therefore points to the right. As the object is accelerating to the right, I will also label the acceleration as moving to the right. The next step in any question like this is to use F is equal to ma, Newton's second law. However, remember, this is a vector equation just like our Suvat equations from the previous lecture. This means that because we are in 2 dimensions here, just like projectile motion, we can apply F is equal to ma in 2 different directions, up and down and left and right. Applying F is equal to ma in the up-down direction doesn't give us any information. Remember, F on the left-hand side of F is equal to ma is net force. In the up-down direction, the net force is 0. Also, the acceleration in the up-down direction is 0 because the object is not moving in the up-down direction. Therefore, applying F is equal to ma in the up-down direction just gives us 0 is equal to m times 0. 0 is equal to 0. Nothing is garnered from that. Instead, we can also apply F is equal to ma in the left-right direction. What is the net force in the left-right direction? What is that capital F? Well, the only force acting in the left-right direction is capital T, the tension. Therefore, writing down F is equal to ma, we get that capital T is equal to 6 times a, the acceleration. Remember, we have to choose a direction for which our vectors are positive. I have chosen the right direction to be positive. If instead I had chosen the left direction, I would have instead got minus t is equal to 6 multiplied by minus a, because a would also be pointing in the negative direction. Minus t is equal to 6 minus a is actually the same as t is equal to 6a. Again, we should get the same answer either way. Great, I now have an equation from using a force diagram on the 6 kilogram mass. However, we have two unknowns. We have capital T, the tension, and we have the acceleration a, which is what we are looking for. Therefore, if we are to answer this, we need to get a second equation. To do this, we will now look at the 4 kilogram mass. The force diagram for the 4 kilogram mass is a bit easier because there is no forces acting on the 4 kilogram mass left or right. The only forces are acting in the up-down direction. The object has a weight capital W, which is pointing towards the ground. And there is also a tension capital T. Again, that tension points in the direction of the string. However, we know that the object is in fact accelerating down, so therefore this capital T, this tension force, must be somewhat smaller than the weight force. If the tension force was equal to the weight force, then there would be no acceleration because there would be no net force. Therefore, I shall draw this tension arrow slightly smaller than the weight arrow. Again, I will label the direction of the acceleration, which in this case is downwards. Now, as before, I can apply F is equal to ma. In this case, I will apply it in the up-down direction. Naturally, there is no reason to apply it in the left-right direction because there is no forces. We would again get 0 is equal to 0. In this case, I will define the down rather than the up direction to be positive. My choice of direction may seem arbitrary, but all I am doing is choosing the direction which has the most arrows pointing in it. We have 2 arrows pointing down, W and A, and only one pointing up to capital T. Therefore, to minimize the number of negative signs we have, I've chosen down to be positive. Again though, if you choose up as being positive, you would get the same answer. Let us first work out the left-hand side of F is equal to ma, the net force. Well, as I've chosen down to be positive, this means that W will be positive and T will be negative. Remember that weight is equal to mass multiplied by acceleration due to gravity, therefore weight is equal to 4 multiplied by g, which is roughly 40, but I'll keep it as 4g for now. Therefore we have 4g minus t, that is the net force on this object in the up-down direction. Weight minus tension. Now we have the net force, and we know from Newton's second law that is equal to mass multiplied by acceleration, therefore that is equal to 4 multiplied by a. Remember, we are looking at the 4 kilogram mass here, so the mass is 4. Now we have everything we need. We have two equations with two unknowns. Remember, we do know what small g is. It is roughly 10 meters per second squared. Therefore, I can sub in that t is equal to 6a into this new equation, and we get 4g minus 6a is equal to 4a. Rearranging, we get 4g is equal to 10a, and therefore a is equal to 4g over 10, which is roughly 40 over 10, or 4 meters per second squared. Therefore, our answer is option D. For the final question, I'm going to repeat the question from before, question 4. However, I'm going to add some more information in it to make it more difficult. This question here is pretty much as difficult as a question in this category would get on the MCAT. Here we again have our 6 kilogram mass on the table, but this time we are no longer told that the table is smooth. Instead, the table has some friction associated with it. Anytime a surface has friction, an object on that surface will slow down as it moves. I will now show you how to deal with friction in this question. We are told that the coefficient of friction for this table is 1/3. The coefficient of friction tells you how good the frictional force is. Again, I will show you what to do with this number as we go through the question. The rest of the scenario is the same as in question 4. We have a string going over a smooth pulley attached to a 4 kilogram mass that is hanging freely. However, the question is, instead of looking for the acceleration, we are told that the object is initially 16 centimeters above the ground. We are then asked how long it takes for this 4 kilogram mass to hit the ground. The reason why this question is more difficult than the last question is twofold. First of all, we have now introduced the idea of friction, and secondly, the quantity we are looking for, time t, does not enter into Newton's laws. F is equal to ma, there is no time there. Instead, what we are going to have to do, as you will see, is first work out the acceleration and then use our Suvat equations. Because remember, acceleration does enter into the Suvat equations. Again, as always with these types of questions, we start by drawing free body diagrams. As nothing has changed about the 4 kilogram mass, its free body diagram remains the same. We have the weight acting down, the tension force acting up, and the object is overall accelerating down. Taking the down direction as positive, we get that the weight force acting down, which is mg, which is 4g, minus the tension because the tension is acting up. And that is equal to mass multiplied by acceleration. Mass is 4 and A is A. And A is positive because it's acting down. I have chosen down to be positive, therefore A is also positive. Now let us draw the free body diagram for the 6 kilogram mass. Again, for the 6 kilogram mass, we have its weight, capital W, and the reaction force, R. We know that these are equal and opposite as this 6 kilogram mass is not moving in the up-down direction. Again, as before, we also have the tension T, which is acting to the right. However, we now also have the friction force. How do we deal with this? What does this mean? Well, the object is still accelerating to the right because the 4 kilogram mass is falling. Therefore, the object is still accelerating to the right. Since friction opposes motion, the frictional force must be acting in the opposite direction to the acceleration. I will therefore draw a force to the left representing the friction. Again, as we know the object ends up going to the right, this frictional force must be somewhat less than the tension force, and I will therefore draw the arrow slightly smaller. Again, we can apply F is equal to ma in the up-down direction and in the left-right direction. Again, applying F is equal to ma in the up-down direction doesn't seem to tell us anything interesting. We get that the net force, which is R minus W, is equal to mass times acceleration, which is 0, because there is no acceleration in the up-down direction. However, for this question, this is actually useful, as we shall see shortly. I can use this fact to actually calculate R, because R, as I just said, is equal to W, and we know what W is because we know the mass. W is mass times acceleration due to gravity. W is equal to 6g, which is 60 newtons. Therefore, because R is equal to W, R is also equal to 60 newtons. Now we have something slightly different in the left-right direction. Again, I shall choose the direction to the right to be positive just because I have more arrows pointing to the right than the left. I have A and capital T pointing to the right and just small f for friction pointing to the left. Therefore, applying F is equal to ma in the left-right direction gives us T minus F, the tension force minus the friction force. Tension is positive because it's in what I've called the positive direction, and friction is in the opposite direction, the negative direction, is equal to ma, is equal to 6a, because the mass for this object is 6 kilograms. I can now rearrange this and we get T is equal to 6 multiplied by the acceleration plus the friction force. Hopefully you can see what the problem is here. We now have 3 variables in this one equation. We would therefore have 2 equations with 3 unknowns. That is not enough equations to answer this question. To answer this, there is something about the frictional force that I have not yet told you. The frictional force of a surface is actually related to the reaction force of that surface. The frictional force is equal to the coefficient of friction multiplied by the reaction force. In other words, small f is equal to mu r. How is that useful to us? Well, remember, for we know what the reaction force is, capital R. Capital R is equal to 60 newtons. We can therefore plug this into our equation. Therefore, we now have T is equal to 6a plus 20, and that fixes our problem because now we have an equation with 2 unknowns. Before we had 3 unknowns, now it's gone down to 2. We now have 2 equations with 2 unknowns. We have 4g minus t is equal to 4a and t is equal to 6a plus 20. Hopefully you feel comfortable solving these 2 equations. For example, for 4g minus t, instead of that t you could put in 6a plus 20. Or what I'm going to do is I'm going to add the 2 equations together. add the left-hand sides together and add the right-hand sides together. The reason I do that is because when I do that, I get 4g minus t plus t, and the t's cancel, so I just have 4g. And the right-hand side, I get 4a plus 6a plus 20, which is 10a plus 20. I now have an equation with only one unknown in it. Remember, g is known, it is 10 meters per second squared. If I rearrange that, I get 10a is equal to 4g minus 20, which is 40 minus 20, or 20. I get 10a is equal to 20, and therefore a is equal to 2 meters per second squared. If you recall from our previous question, we got that a is equal to 4 meters per second squared. Hopefully getting a smaller number makes sense to you. Because there is friction now, this system of objects will move slower. They will accelerate slower. However, we are still not done. We have found the acceleration, but the question is asking us to find the time it takes for the 4 kilogram mass to hit the ground. How do we do that? Well, we haven't used some information we are given in the question. We are told that the 4 kilogram mass is initially 16 centimeters off the ground. Also, we are told that initially the object is simply released. That means initially its initial velocity is 0. The object is not pushed towards the ground, it is just let go. The initial velocity is 0. Therefore, thinking about our Suvat equations, if I consider the down direction as positive, then we have that the acceleration is 2 meters per second squared. We have the displacement as 16 centimeters, but because we have the acceleration in meters per second squared, we have to convert this to meters, so we get 0.16 meters, and we have the initial velocity 0 meters per second, and we're looking for the time. Therefore, we know A, we know S, we know U, we know T. We want to use the Suvat equation that does not have the final velocity V in it. This equation is S is equal to ut plus a half at squared. Subbing in what we know, we get that S, which is 0.16, is equal to ut, that's 0 because u is 0, plus a half a, which is 2, multiplied by t squared, which is what we're looking for. This simplifies down quite nicely, as we have a half multiplied by 2, which is 1, so we simply have t squared is equal to 0.16, and therefore t is the square root of 0.16, which is 0.4 seconds, and therefore the correct answer is option A. So, one important thing you should take away with this is how to deal with the frictional force. Remember, the frictional force opposes motion, and therefore when you are drawing its vector, always draw it in the direction opposite to which the object is accelerating. The frictional force is proportional to the reaction force, and that proportionality constant is equal to the coefficient of friction mu. And finally, anytime there is a question concerning a system of objects, always draw free body diagrams for each object. Do not try and put them all in one diagram, it will get very messy. Draw separate diagrams for each object. So wrapping up, what have we learned in this lecture? Well, I recalled that force and acceleration are both types of vectors. I then used Newton's laws to relate force to acceleration. The first law told us that an object will not accelerate unless a net force acts upon it. An object that is at rest will remain at rest unless a net force acts upon it. Also, an object that is moving with constant velocity will also remain at that constant velocity unless a net force acts upon it. In other words, a net force causes acceleration. It does not cause velocity. That is a common mistake a lot of people make. Net force causes acceleration. An object can be moving without a net force acting upon it. Newton's second law then gave us the direct relationship between force and acceleration. It told us that force is equal to mass times acceleration. That is a vector equation, and therefore when we actually apply it, we have to apply it in each dimension separately. Newton's third law then explained the contradiction that seemed to arise from the second law. Newton's second law told us that the net force on an object is equal to mass times acceleration. However, an object sitting on a table is not accelerated towards the ground, even though that object has weight. The reason why that is the case is because there is an equal and opposite force that keeps the object where it is. That is the reaction force, capital R, that is exerted by the table on the object. I then discussed the importance of drawing free body diagrams when answering questions on the MCAT. Doing this not only helps you visualize what is going on, but it is also important so that you know which vectors are considered positive and which are considered negative. Finally, I also talked about torque, which is the rotational version of force. To work out the torque, you multiply a vector by a vector, in other words, you use a cross product. In general, for the MCAT, the most common type of questions that come up from this section is to do with free body diagrams. Please continue to practice questions involving free body diagrams until you feel comfortable with answering questions on the MCAT. Thank you guys for listening, and I will see you guys in the next video.